In a previous episode of Evolving Code, I suggested you to use the language features at a higher level of abstraction than those at a lower level of abstraction whenever possible. The reason was simple. It would be easy to evolve your application with the evolution of the language. This means less time and effort are required to maintain your application, which implies lesser maintenance cost. Does that mean we don't have to put effort into learning the lower level of abstractions available in the language? Absolutely not. By peeling off the abstractions and understanding the under the hood details, developers will be better positioned to make impactful design decisions. For example, you will be better positioned to decide how to trade off a few CPU cycles to save some memory space, or how to save a few CPU cycles by trading off memory. Let's find out in this episode of Evolving Code how Java stores integer data types by understanding one of the least memory consuming data types, that is byte. Hello and welcome to Evolving Code. My name is Naresha. Java provides several data types for representing integer values. When I say integer, I am referring to the mathematical concept of integers. So Java provides byte, which is the smallest type, which requires only 1 byte of memory space. Then there is short, which consumes 2 bytes. Then we have int, which consumes 4 bytes, and then we have long, which consumes 8 bytes. If by using any of these types, if your data is like too large to fit in 8 bytes, then you could make use of big integer class available in Java. With this information, let's focus on byte and understand how Java stores integers in byte type, which in turn will help you to understand all other data types as well. So let's go to our IDE and create a few variables of byte type. Here we have created a variable called number, which is of type byte, the primitive type, and we have assigned a value which is 1, and then we are trying to print the value of number. Let's run this piece of code. As expected, you see it's printing 1. Now let's make the change the value assigned to variable number to 10, and let's run the program. Again, you see it changes to 10. So far we have assigned the value in decimal, which is default, and when we print, also the value gets printed with radix 10 or as a decimal value. Now that we have seen how byte data type works, how the value gets printed, let's focus on understanding the representation of byte type inside the memory. You're already familiar with the fact that a computer represents values using zeros and ones. Here we have 1 bit of memory. The bit value can be either 0 or 1. So by using 1 bit of space, we can store 2 values, which is 0 or 1. Now how many values we can store if we have 2 bits of space? So as you could see, we can store the values 0 0 0 1 1 0 1 1. That means we can store total 4 possible values using 2 bits. 4 is 2 to the power 2. Then if we increase the size to 3 bits, we can store 8 different values, and 8 is 2 to the power 3. So if we have 1 bit, we can store 2 to the power 1 values. With 2 bits, we can store 2 to the power 2, which is 4 values. With 3 bits, we can store 2 to the power 3, which is 8 values. Now coming back to the byte data type, 1 byte means 8 bits. So with 8 bits, we can store 2 to the power 8, which is 256 values. That means a byte can represent 256 different values. Let's take few examples of some positive integers, how we can store with the 8 bits or 1 byte. As you could see on the screen, we have 8 bits here. Number 1 can be represented with the last bit being 1 and all other bits of the byte being 0. Now with 1 0, we are storing the value 2, and to store value 3, the last 2 bits will be 1 1, all other bits will be 0. Now going this way, if you make the 7 bits as 1 with the leftmost bit being 0, we will represent a value of 127. So let's go to our IDE and change the value to 127 and see if it prints 127. I have changed the value to 127. Let's run this code. It's as expected, it is printing 127. Now if I change the value to 128, immediately it shows an error. What is the error? It says that required type is byte, but we have provided int. What's happening here? To understand that, let's use one of these classes available in Java, which is the wrapper class for byte primitive type. Let's go there. Let's say byte dot max value. You would see it is 127. Let's just go ahead and print that value. Similarly, we will print the minimum value. So let me change it back to 127 so that compiles and works as expected. So now you would see that maximum value is 127, minimum value is minus 128, and the number is 127. So with the byte size of memory, even though we can store 256 possible values, Java is treating it as a signed value, not as unsigned value. So thus we are able to store from minus 128 to 127. So far we have seen the memory representation, the binary memory representation of positive numbers. Let's see how negative numbers are getting stored under the hood in that 1 byte space. Whenever we are representing a signed number in computers, we make use of the most significant bit of the data to represent whether the number is positive or negative. The most significant is the one which is the leftmost bit in the data. Since we have only 1 byte of data, it is the 8th bit if you count from right. So rightmost will be the least significant bit and leftmost will be the most significant bit. If it is 0, it is treated as positive. If the value is 1, then the number is treated as negative. Let us see how we can encode negative numbers. You are already aware of how to encode positive numbers. On the screen you are seeing the representation for plus 1, which is all 0 bits except the last one, which is 1. So to start with, we have to take the data bits and get the ones complement of the number. We get ones complement of a number by replacing zeros with ones and ones with 0. So here you would see 0 has become 1, 0 has become 1, and at the end 1 has become 0. We have 2's complement. Now we need to get the 2's complement of this value by adding 1 to the 1's complement value. So you would see 1 1 1 1 1 1 0 plus 1, that means everything becomes 1, and the most significant bit will become 1 because it is a negative value. So you could see we have a value. We first take 1's complement by replacing zeros with the 1's, and we get 2's complement by adding 1 to 1's complement. So now this 2's complement is actually the representation of negative 1, while positive 1 is represented like this. Negative 1 is not represented just by replacing the most significant bit with 1, but also by converting the value to 2's complement. So finally, with every bit being 1 represents negative 1. Now you might be wondering why computer systems makes use of 2's complement to represent negative numbers. Can't we just change the most significant bit to 1 and keep all other bits the same as their positive value representation? That is because of the computing efficiency reason. We will see why that is required. For that, let's take the example of addition. So if you take numbers minus 1 and plus 1 and minus 1, add them, we will get 0. So let's take the plus 1. You would see we have already seen the representation of plus 1 earlier. We just saw how to represent negative 1, which is all ones. Now if you add these numbers 1 plus 1, which will be 0 with carry 1, then add that carry to this, it will become 0. Keep on adding with the carry here, you will get 1, and add that 1 to the most significant bit, you will get 0 with the carry 1. We don't have to worry about that carry. Now we have every value is 0 here, which means we have the representation of 0. So this is the benefit of using 2's complement. So you don't have to worry if the number is positive or negative. We could add the numbers together and get the result as if they were both positive or as if they were both positive. We don't need any special if else consideration to see if the number is negative. In that case, the computing would become very costly. By representing negative numbers in 2's complement form, we have made the computing very simple and very cost effective. Feel free to take any other numbers and have their 2's complement representation and add them and confirm this for yourself. Let's take another example where the result is negative. So we have minus 1 and minus 4. If we add them, we should get minus 5. So we have minus 1 representation here. We have minus 4 representation here. You take 4, take 1's complement, add 1, get 2's complement, you will get this number. Then finally if you add, you will see you will get this number. How to check if this is -5? You again do 1's complement and add 1, take the 2's complement. So if you take 1's complement, you will get 1 0 0 here. 1 0 0 is 4, 1 0 0 plus 1 is 5, and MSB is 1, which is negative, so it is -5 what we have here. Now that you understood how byte data type stores signed integer values, you could make use of this knowledge to understand data how data is stored in memory for data types such as short, int, and long. While byte type was just occupying 1 byte of memory, short will make use of 2 bytes, int will take 4 bytes, and long data type will use 8 bytes of memory. It's just that they are capable of storing larger integers. In the part 2 of this topic, we will explore more fundamental details about byte type. I hope you found this episode useful. Thank you for watching and see you in the next episode.